Namaste everybody, and welcome to this lecture on mathematical foundations for machine learning. We are in the last week of the course, and we are currently looking at the idea of clustering, classification and regression. So what I am going to do is, in the last couple of classes you would have seen Dr. Ashok Rao's lectures on clustering and classification. I will be doing the ideas of linear regression and logistic regression, and in this lecture we will look at linear regression, and in the next lecture we will look at logistic regression as such. So before we get into the idea of linear regression, what it means, I am quite sure most of you know, at least from the high school perspective, where you fit a straight line for the given data. What we are going to do now is, like, I am just going to revisit some of these concepts that you have studied probably in early classes, maybe school time, like in class 11, 12 when you did matrices and things. So I will be looking at that a bit, and then we will get to the idea of this linear regression, though we have done the line of best fit, least squares, ideas, all those things we have done, but we are taking this a bit again, where we are going to give meaning to all that we have done in terms of our least square solution that we found. So we are going to give meanings to it, or we are going to give interpretation to those things when we do linear regression, which is also trying to fit a straight line for the given data. And what we are going to do is we are going to look at it a bit in a statistical manner, and then we are going to say that this is what it finally boils down to. That means when you looked at your pseudo inverse A transpose A, the whole inverse A transpose Y, in order to get the least squared solution, we are going to come back to the same thing again. We are going to come back to the same thing, and then what we are going to say is, look, if when you do this A transpose A, the whole inverse A transpose B, what we have actually is, I mean, those terms which are there in the matrices, we are going to give a proper statistical meaning. So that is going to be the focus of this lecture. So let us look at this. Remember, sometime when you were doing your class 11 or class 12, when you did the first course on matrices, somebody would have told you, like, prove that the determinant of this matrix, like A, is A minus B into B minus C into C minus A, where A is this matrix 1 A squared, 1 B squared, and 1 C squared, right. This is a matrix that you would have studied in your high school level, where they have told you, like, look, why don't you try to do the elementary row operations, and then get the prove that the determinant of this matrix A that is given here is equal to the this product A minus B into B minus C into C minus A. Now at that time when we were doing, we were probably not either given what is the use of this matrix, or probably we were just told, look, you compute the determinant so that if you solve it properly, you are going to get a 6 marks or a 10 marks in your exam. Now what does this matrix do? Let us first of all figure out what this matrix does. We will try to understand this, and then we will come to the idea of regression that we were looking at, right. So okay, fine. So let us take a simple case here. Suppose I tell you, look, I have a function, I do not know, I have a function, let us say we have a function or let us say we have a polynomial, that is better. Suppose we say that we have a polynomial of a polynomial, let us say p of x is equal to, let us say, a naught plus a1 x plus a2 x squared. What I'm going to say is, look, I don't know what the values of these, what are the coefficients a0, a1, a2, I don't really know, but all I know is, I know that the function values, we have a polynomial whose parameters a0, a1, a2 are not known, a0, a1 and a2 are not known, right. However, what is known is the following. What is known is, let us say, P of let us take this, x is equal to a is nothing but a0 plus a1 into a plus a2 into a squared. Let me call that to be equal to, let us say some y a, saying that the p of x at x is equal to a, I am going to call that as y a. So, let me also put this, p of x is equal to b is basically a0 plus a1b plus a2 b squared. I am going to call that as yb, and p of x is equal to c is basically a0 plus a1c plus a2 c squared. And let me call that as yc. So, what do we have here? I give you the points a, b and c, and I tell you at the point a, x is equal to a, the polynomial p of x or the function p of x takes the value, let us say y a, and at the point b, x is equal to b, the function takes a value y b, and at the point x equal to c, the function takes a value y c. Now, these are the only thing given. So, what is given? We are given x comma y, where x comma y is nothing but, when x is a, the function is y a, when x is b, the function value is y b, and when x is c, the function value is y c. Now, what we want is, we want to find out that quadratic curve which passes through these 3 points, a y a, b y b and c y c. So, how do we do this? So, let us look at this. So, let us write this whatever that we had here, let us write this 3 equations in terms of a matrix. Let us see what happens. So, I have y a, y b and y c, which is nothing but, what do I have here? The coefficients that I want to find out, these are the unknowns basically, a0, a1 and a2, these are unknowns, and these are the parameters for the polynomial or for the quadratic curve. So, I have a0 plus a1a plus a2a square, a0 plus a1b plus a2b square, a0 plus a1c plus a2c square. Now, we see something interesting. What is that? This is the same matrix that we looked at in the previous case. When we started this lecture, we looked at the same matrix. So, we have this matrix which is repeated here, and what it says is, look, if the determinant of this, let us say we call this as y is equal to ax, if determinant of a is not equal to 0, then we have a unique solution, we have unique triplets a0, a1, a2 as a solution for this y is equal to ax, right, unique solution a0, a1, a2, that is basically the solution that we have, right. Now, that is exactly why we said that, look, the determinant of a, prove that the determinant of a is a, this matrix is a minus b into b minus c into c minus a. That means, what do we essentially say? We say that, look, I need to look at what I do is I take 3 different points here. What are the points? X equal to a, x equal to b and x equal to c. Suppose if I take x equal to a, x equal to a and x equal to c, then you will see that the first row is 1AA square, the second row is 1AA square again. That means the determinant of this matrix becomes 0, therefore you will not be able to get these coefficients. Now what happens if the determinant of A is not equal to 0, then we say that we get a unique solution. That means we can say that there is a unique quadratic curve that passes through these 3 points, curve that passes through these unique points. What are the points? A comma B comma C, and taking those values, which is taking values YA, YB and YC respectively. So what we have now, we now see very clearly that, look, okay, you can actually use this matrix idea to fit a curve. Now what we want to see is, fitting a curve is basically you are given A naught and A and YA, B and YB and C and YC. You are trying to find out what is the relation between your what you call X and Y, right, where X is basically the input variable and then Y is X in this case is, okay, let's not confuse this, so we'll take this as okay, we'll just take this as this corresponds to my X vector. Now I just wanted to say why Ax equal to B type, so I've used this, so don't get confused between what I'm saying, that X and this X corresponds to this, right. Now whereas here what we have done is we have basically given those points X comma Y, we have taken this to be A, B and C. So these are the points that I'm talking about right now. Okay, so what do we do here? We see that if you have 3 distinct pairs of points, then you can fit a unique quadratic curve. That means there is only one unique curve which passes through, because the determinant is going to be non-zero here. Now so the first of all, we also now understand that, look, I can use matrix and things to figure out the models for a curve. Like if I can fit a curve, if I want to fit a curve, what I will do is I will use the matrix methods to find the coefficients of my what do you call the terms there using matrix methods. Now what we want to do is, in statistics, when you look at, especially in case of data science, you always want to determine some kind of relationship between a pair of variables, right. In this case it explicitly says that, look, I have a quadratic function, find the parameters corresponding to the quadratic function. But in the in our case, what we have, like when you collect data, we really do not know what is the kind of relationship that exists, right. So in that case what we do is, though we want to kind of find out what is the relationship that exists between, let us say, the input variable X and the response variable Y, we cannot really we do not really determine, in the sense we do not try to play around with both the variables at the same time. Instead what we do is, we keep one of the variables, we keep giving values, we fix up one of the variable at a particular value. Let us say if we have let us say X comma Y. Now what I do is, I will take my X to be the input variable. That means this is going to be my independent variable. This we call as independent. That means it can take values apni marzi. So it can take its own, you can fix any value for X and then see what is the effect of this X on that particular on that particular other variable, right. So what we are going to do is, in this case we are going to call the input variable to be the independent variable, and we say the Y values is going to be the output variable, and we call this as the response variable. Right. So this is going to be the response variable. Now what I do is, the moment I am given this what do you call the set of data points, let us say x1, y1, x2, y2, x3, y3, etc., xn, yn. Now what you do is plot this, see what is the trend that you can check. Now what we want to do is the first simplest thing that I can look for as a relation between y and x is basically figure out whether there exists some kind of a linear relationship or not. So what we do is, suppose I take my x value to be fixed at say some xi, then the corresponding y variable will be, y value will be say yi. Now what we are going to do is we want to check for different x, we are going to collect different y, and then what we are going to say is plot this and see if you can fit a straight line. Now the moment you see if there is going to be a linear relationship, all you need to do is find out the coefficients of that straight line. Now the problem that we have here is you are not just going to work with 2 points, because you know that if you are given 2 points or 2 distinct points, you can actually fit a straight line. Now in our case of data science, where we have huge number of points, we really do not know whether there will be one straight line which is passing through all the points. That would be a most ideal case or the best case possible for us, because it does not skip any of the points, but in real life it does not happen so. So what happens is you may have set of points which are like this. Let us say I have this variable x and I have this variable y. I could have some points like this. We do not even know. Now somehow I feel, okay, can I get a trend which looks like linear? Of course I can actually find out that, okay, it probably looks linear in an average sense. So what I do is, the straight line that I try to fit may not pass through all the points. That means there is going to be all kind of error, and that is precisely where we get into the idea of least squares and stuff. So what we are going to do is, let us take up this. So we are going to make some statements here. So let us say let the input variable, let the input variable be x. I would say instead of saying input variable be x, I would say that input variable x, it's the value that you are going to fix it up. Okay, input variable be set to a value x. Right. So what I am going to do is I am just going to set the input variable to a value x. Okay. Now what I am going to do is, we have the response variable. So what we are going to do is let, you probably note the difference here. I have used a lowercase x and then an uppercase y. So I will tell you why we have used this. So let y be the resulting value of the dependent variable. So now what we want to see is, we want to see whether there is a simple linear relationship that exists between these 2 pairs of variables, right. So what we want to do is, we want to check. So we will say that, look, the simplest relation between x and y is a linear relation, right, is a straight line or a linear relation. Which is of the form, let us say y is equal to, we will take this as beta naught plus beta 1 into x. So now what happens, once you know the values of once you determine the values of beta naught and beta 1, then what it does is, the model actually tells you that, look, it is possible for us to predict the exact response for the corresponding input value, or for any input value x, you will be able to predict what is the exact response. However, you see that when you collect data, you get both x and y. Now and then you fit this straight line model. So the straight line model, or whatever straight line that you fit, is not going to pass through all the points, therefore it is going to miss a lot of those y. Therefore what happens, at the corresponding x, instead of getting a y you may actually get a y hat. Is that correct? That means there is going to be, okay, so what we do is we will say this. So, once the values of beta naught and beta 1 are determined, basically this is the model that we have. The model parameters are beta naught and beta 1 determined. The model supposes that it would be possible for us to predict the exact response for any input variable, right, for any input value, exact response for any input value. Right. Okay. So, now, but there is a problem here which I discussed already. The problem is that the what would you say is like it is impossible to predict, with highest accuracy the values of y. Right, because you can never attain that kind of a precision. So, what happens is like there will be some kind of a random error. So, what we say is we will say that look, this y is equal to beta naught plus beta 1 x is valid subject to say some random error, subject to random error. So, what we are going to have? We are going to have y is equal to beta naught plus beta 1 x plus the error term e. So, the model parameters are basically beta naught and beta 1, and the error is basically e is the random error, and what we assume is the random error has mean 0. Random error is mean, it is a random variable with mean 0. Right, we have this with mean is equal to 0. Now, once you get this, what we are going to do is we are going to look at finding out this model parameters, right. So, what is it we are going to say? The first thing we are going to say is, so we are going to define the idea of linear regression here. So, what we say is linear regression is nothing but linear regression, it is the relation between y and x given by y is equal to beta naught plus beta 1 x plus e. This is basically what we call as linear relation, and what we say is for any value of x, y is going to be a random variable. So, what we say is for any value of x, y is going to be a random variable, y is a random variable with mean E of y is equal to beta naught plus beta 1 x. We already know that expected value of E is going to be 0, because that mean we have already taken it to be 0. So, what we do is, so this linear regression model that we have here, it supposes or it says that a straight line, okay, so what we will do is we will just say it supposes a linear relationship, a linear relationship between the mean value of the response variable, between the mean value of the response variable and the value of the input variable. And so we really do not know the values of, let us say, beta naught and beta 1, and that has to be estimated from the data, right. So, beta naught and beta 1 are typically not known, are typically not known and need to be estimated. And estimated from where? Estimated from the data. So, how do we do this? That is what we are going to check now, right. So, what you do is, the moment you are given pairs of data, let us say this, consider data pairs. Data pairs, let us say x1, y1, x2, y2, etc., xn, yn, right. I have this x1, x2, xn, the function values at x1, x2, xn. So, that is basically what is given to you, right. So, what does this mean? This means that if the input value is set at x2, if the input value is set at x2, then the response or the observed value of the output is y2. This is what we have. So, now what you do is, the moment you are given this pairs of data, what you do is, first of all you plot. So, what you do is plot the data to see, basically you try to visually examine the data to check if, of course within some random error, if let us put this subject to a random error, a straight line can be fit, a straight line relation between x and y appears. Of course, you do have some assumptions and all those things, a couple of what do you call, assumptions that you can do, which you will do in any statistics course. You will talk about, there is no multicollinearity and stuff, we will not worry about it right now. So, but just let us take this, okay. So, what we are going to do is, we are going to estimate the regression parameters, which are here basically the beta naught and beta 1. So, we are going to do, to estimate let us say the regression parameters. So, what we do is, we will take this, let yi be the response corresponding to the input variables, let us say x1 corresponding to the input variables, let us say x1, x2, etc. xn. That means the values of the input variable is going to be x1, x2, xn, and yi be the responses correspond for I is equal to 1 to n. So, we are going to take that, right. So, I would actually put this as I is equal to 1 to n here, so that it becomes clear. We say I is equal to 1 to n is the response that you would get for the input variables taking when it takes a value x1, the output is y1, it takes value x2, output is y2, and so on, right. So, this is what we have. Therefore, what we have is the regression model, which is going to look like this. So, we use this data to obtain the model parameters, beta naught and beta 1 of simple linear regression model where the model is given by y is equal to beta naught plus beta 1 x plus the error. Now, what are we going to do here? We are going to look at something interesting in this case. So, if you want to estimate beta naught and beta 1, there is not going to be one unique beta naught and beta 1 which is going to pass through all the points that you have taken, and therefore, what we do is, and we do not have the complete data also. So, what we do is we try to predict, we try to estimate the parameters beta naught and beta 1. So, what we will do is we estimate, we try to determine the estimators for beta naught and beta 1. The estimators for beta naught and beta 1, and let us say that the corresponding estimators are beta naught hat and beta 1 hat. These are the estimators for beta naught and beta 1. Right. So, then what we have? We have this. So, what happened then, because it is not a single value, you are going to get the best estimate for beta naught and beta 1. So, what is going to happen is, you see that with beta naught and beta 1, I would get this y hat, which is basically the estimate for y, which is given by beta naught hat plus beta 1 hat x. This is basically this is the estimate for y using that model, estimator of y. The actual y is basically the actual observed value is this y, and this is from the model. So, there is going to be a difference that is going to exist. So, what we will say is since, so I will say yi hat, every value of this y. So, I will say yi hat is equal to beta naught hat plus beta 1 xi, beta 1 hat xi, because xi is like, these are the points at which you are going to evaluate. So, this is fine, right. So, since yi is the actual response which we have actually got or which we observed, right, and yi hat is from the model, there is going to be an error. We have an error given by what is the error? Error is going to be for every value. So, I am going to give epsilon I to be the error, which is given by the actual value yi minus the estimate for this yi, which is like the yi hat. So, I am going to write this minus of beta naught hat plus beta 1 hat xi. Right. Again, you can, I mean, for all I is equal to 1 to n. Now, what is the requirement that we have? The requirement is, so what do we need to do? We need to choose the estimators, beta naught hat and beta 1 hat, in such a way that in order to minimize, by now you would have been I mean you would have clearly understood the idea of least squared error and so on. So, what we are going to do is we are going to do this I is equal to 1 to n epsilon I squared error, because you can get a minimum and all those things. So, what we do is we take this. So, this resulting estimator is basically a least squared estimator. So, this is nothing but least squared estimator. Now, how does that look like? So, let us take up this. I have my data points, this is basically x and that is basically let us say y. The actual data points are basically this, let us take 1, let us take 2, then 3, so let us say I have like 4 points. Now, what I am going to do is I am just going to say that okay, with for this 4 data points which are basically let us say x1 y1, x2 y2, x3 y3, x4 y4. These are the points that I have. Now, what I am going to do is I am going to say I am going to use this regression and then I am going to fit a straight line like this. This is basically the line of best fit which is given by beta naught hat plus beta 1 hat xi, right. So, now what we see is we see that the error, you are going to look at the error here, this is nothing but epsilon 1, this error is going to be epsilon 2, this error is going to be epsilon 3 and that error is going to be epsilon 4, right. This is what we have. Now, what do we say? We say that the ensure that the sum of squared of this error is basically minimum. And the moment we get into this, we already know what to do. So, I would just leave this as a small task here. So, I would suggest that okay, task prove that beta 1 hat is given by sigma I is equal to 1 to n xi minus x bar into yi minus y bar. I will change these were all these were all like y1, y2, y4, y3 and I think here also I have yeah. So, I have taken this. So, this is beta. So, I have this. So, what I have is xi and yi minus y bar divided by sigma I is equal to 1 to n xi minus x bar the whole square and beta naught hat it is equal to y bar minus beta 1 hat x bar, where y bar is sigma yi by n, I is equal to 1 to n and x bar is sigma xi, I is equal to 1 to n divided by n. Now, what am I going to do? I am going to do a small thing here. This you would have done it at an earlier classes, but then I am going to do it the linear algebra way, where we will try to interpret our A transpose A, the whole inverse A transpose B. I am just going to do where there is only one response variable and there is one explanatory variable or the independent variable. You can do it for multilinear regression too, right. So, what I am going to do is I am just going to take a simple case where there is only one variable x and independent variable, the other dependent variable is going to be y. So, what are we going to do? I am going to have this. So, let us look at this. So, turn to linear algebra. Okay, so what we have is we are told that look, I have this y hat which is given by beta naught plus beta 1 x. Now what I want to do is find out the best estimate, find out the most optimal values for beta naught and beta 1. So let us call them as beta naught hat and beta 1 hat, such that the squared error is minimized. The squared error is least. Now the moment we say we are going to look at least square, so let me take n different points for this and then see what I am trying to tell. I am going to have these function values y, let us say we have this let us say y1, y2, etc., yn. These are the n observed values that we have, and we just want to fit a straight line. So what I am going to take is I am going to take 1 x1, 1 x2, 1 x3, etc., 1 xn. These are the n points that I am going to look at, and the values that I am going to have are beta naught and beta 1, right. And this is a matrix which is let us say n by 2 matrix, n rows and 2 columns. So this matrix will be invertible if the columns are linearly independent, right. So what we are going to say is we are going to say that if there are at least 2 distinct values of x, then the columns will become linearly independent. The columns of, let me call this as the matrix A, this is y and this is x. So the columns of A are linearly independent. The moment you say they are linearly independent, then I am going to have rank of A to be equal to 2. This implies rank of A is equal to 2. And the moment you know that this is a tall matrix with rank is equal to number of columns, and I want to find out the least squared solution, I already have it. What is that? I know the optimal values, which are basically beta naught hat, beta 1 hat, which is given by A transpose A the whole inverse A transpose y, right. That is what we have, right. A transpose A the whole inverse A transpose y. Now let us figure out what is A transpose A in the first place. A transpose A is nothing but this matrix 1 1 1 etc., 1 x1 x2 etc., xn into 1 1 etc., 1 x1 x2 etc., xn, right. So what is A transpose A? This is nothing but, this is 1 transpose 1, this is 1 transpose 1, this is basically the 1 vector, 1 transpose is basically the vector 1 corresponds to all component 1. So this is 1 transpose 1, then I am going to have 1 transpose x, and then I am going to have 1 transpose x again, and I am going to have x transpose x. So this is the matrix that I have, and I can write this as what is 1 transpose 1, it is 1 plus 1 plus 1 plus 1 etc. n times. So this is going to be n, this is going to be 1 transpose x, this is also going to be 1 transpose x, and this is going to be x transpose x. What is A transpose y? I want to figure out what is A transpose y. A transpose y is 1 1 etc., 1 x1 x2 etc., xn, and y is nothing but y1 etc., yn. This is nothing but 1 transpose y, and then I am going to have x transpose y. So this is what I have. Now I know that the parameters are basically beta naught hat and beta 1 hat, which is given by A transpose A the whole inverse into A transpose y, A transpose A the whole inverse is I have to find out the determinant. The determinant is basically given by if you look at the determinant of this matrix. So let us do this. A transpose A the whole inverse is nothing but 1 by n times x transpose x minus 1 transpose x the whole square into, I have to change the swap the diagonal elements x transpose x and this is n, and I am going to change the sign of this, which is minus 1 transpose x minus 1 transpose x. This is what I have. So now what I do is I substitute all these things here. I am going to get this 1 by n into x transpose x minus 1 transpose x the whole square into x transpose x minus 1 transpose x minus 1 transpose x, this is going to be n, into A transpose y is 1 transpose y x transpose y. This is what we have, right. Now what I am going to do is I am just going to do a small thing here. So from here we can even find out what is beta naught and beta 1, but I am just going to do a small what do you call, I am just going to do a small jugaad here. What I am going to do is I am going to multiply and divide, I am going to multiply and divide by n square, multiply the right hand side, multiply and divide RHS by n squared. So what am I going to get? I am going to get the left hand side will remain this beta naught hat beta 1 hat. So that is going to be n squared by n into x transpose x minus 1 transpose x the whole square, and this divided by n squared, what I am going to do is I am going to divide this matrix all the terms by n and divide all the components of this matrix by n. So that will give me n squared. So I am going to get x transpose x by n minus 1 transpose x by n minus 1 transpose x by n, and this is going to be n by n. So this is going to be 1, and here what I am going to have is 1 transpose y by n, and this is going to be x transpose y by n, right. This is what we have. Great. Now if you can, if you clearly look at what it is, I am going to do something here. Let me just make a small thing about this this scalar that I have here. This is just a scalar. So what I am going to do is I am going to look at this. So n squared, I will bring it down. So what I am going to do is I am going to divide throughout by n squared there. So I am going to get 1 divided by x transpose x by, we are going to have n squared minus 1 transpose x by n the whole square. This is what we have, and rest of the matrix will remain the same, right. Now what is x transpose x by n squared? What is x transpose x? This is basically x1 squared by n squared plus x2 squared by n squared and so on, right. So what are we going to have? This is going to, oh, this is divided by n squared, so this become n, sorry. So this is going to become n because you have n x transpose x by n squared, so this is going to become n. So this is something like saying, look, x1 squared plus x2 squared plus x3 squared plus xn squared by n. What is that? That is the expected value of x squared, or that is the mean squared value, right, mean of the squared value. So I am going to call this as 1 by, I am going to call this as the root mean square. Root mean square is you take the square root of x transpose x by n. So what I am going to do is, but this is going to be x transpose x, the whole it is nothing but x1 squared plus x2 squared, there is no square root term involved here. So I am going to call this as root mean squared of x squared minus, what is 1 transpose x by n? This we already saw when we saw sample geometry. We figured out that x transpose 1 by n is nothing but x1 plus x2 plus x3 plus xn divided by n, which is nothing but the average of x the whole square. That is what we have here. And let us look at these terms. This is again x transpose by x by n, which is nothing but the RMS of x square, RMS of x the whole square. 1 transpose x is nothing but average of x. This is also average of x, of course with a negative sign. This also has a negative sign. Then this is going to be simply 1, and what about this term 1 transpose y by n, that is nothing but average of y, and this is going to be x transpose y divided by n, we will take it this way. So now what we have done is the A transpose A, the whole inverse A transpose, we have actually given a meaning to each and every component that comes here, where everything looks like this, RMS, average and so on, right. So this is what we have. Now what we can do is you can do some what do you call simplification here, and you will end up getting, when you do, I would request you to do simplification here, because for want of time I am just skipping this because it is already about 50 minutes over. So I would just give you the value. I am going to get beta 1 hat is nothing but standard deviation of y divided by standard deviation of x into the correlation coefficient, where rho is the correlation coefficient, and then beta naught hat is nothing but, you are going to have that is nothing but y average of y minus beta 1 hat into average of x. And if you look at what we had written there before, the two values, this is exactly what we have here, y bar minus beta 1 hat x bar, and beta 1 hat is nothing but x minus x bar into y minus y bar divided by sigma x minus x bar the whole squared. So this is what we have, and that is exactly the expression that you would see here. So what we have done is, basically in this lecture we have actually tried to look at the idea of linear regression from both perspectives of statistics, where you are trying to do your x minus x bar and other things, and the other thing that we have done is we have tried to figure out, or we try to relate the idea of least square solution that we saw in terms of our matrix theory to find out the regression coefficients. We use the same expression where we had this A transpose A, the whole inverse A transpose y, and A transpose A, you call it as the Gram matrix, and you can actually work out and you will get to see that these are the coefficients, these are the terms that you have, where the correlation coefficient is basically given by x vector minus, wherever I write x, it is basically a x vector. So this is going to be x minus average of x into 1 the whole transpose, this is the one component vector, so I write it as 1 all 1, then y minus average of y into the vector, one vector which has all the components to be 1, divided by n times standard deviation of x standard deviation of y, and you also make use of this fact. So what we will see is we will see that the standard deviation is basically given by the deviation vector, which is nothing but x vector minus average of x into 1 divided by square root of n. Oh, I should use this, sorry, this is going to be lowercase n. Square root of n. Therefore our what do you call, our regression that we have, which is basically y hat is equal to the average of y plus rho times standard deviation of y divided by standard deviation of x into x minus average of x. This is what we will have. I would also suggest that you go through the following textbooks, because I have used the materials given in the textbook for the second half of this topic, whatever we have done. These results I have used the textbook by Stephen Boyd on the book titled Introduction to Applied Linear Algebra. And for this part, basically the estimators, and for this I've used this textbook, which is Introductory Statistics by Sheldon Ross. So for this initial part I have used so you can refer Introductory Statistics by Sheldon Ross. So when we come back for the next lecture, we will look at logistic regression, and with that we will wind up the week 12 classes, right. Okay, so in this class what we did is we just looked at the idea of linear regression. What is it to say linear regression? Find out if there is going to be a simple straight line relationship between the input variable and the response variable, and then we looked at the linear algebra. Wherever we have done the least square solution, we looked at that, and then we tried to connect these two things and then put everything in order. So what we will do is when we come back in the next class, we will look at logistic regression. Namaste.